Okay. Hey, welcome to the talk, and thank you for joining me. So, this talk is about optimizing multi-threading performance. So basically, I would want to talk about the factors that actually affects multi-threading performance. And in general, I really want to look into the fault sharing and something came from the standard, which is hardware destructive interference for the specifically fault sharing. So before that, I just want to introduce myself. So my name is Shivam, and I work for KDAB, uh, and I contribute to LLVM compiler infrastructure. Recently, I involved in libcx6 stuff in LLVM. I was Google Summer of Code student this year too, working with LLVM as well. And yeah, I'm a student by the way. This is my final year, so bachelor's. And I'm really fascinated about particle physics and cosmology. So if anyone would like to talk about these things to me, please feel free to talk about. Yeah, the outline of the talk is a bit of introduction of multi-threading and when not to use it, because and I really feel when not to use it, it's much more important than when to use multi-threading. Uh, and the factors that affect performance of multi-thread code. And then yeah, we'll look into fault sharing much deeply. Okay, let's start with having a fun analogy. So the busy kitchen. Imagine you're running a restaurant, and imagine you're a single chef in the restaurant. And you have a lot of customers. So customers will, there are many customers in your restaurant, and you're the single chef. So you have to prepare all the dishes yourself. And how would you do that? You will proceed sequentially. So you would make a dish, serve to your customer, then move to the next dish, prepare it, serve to the customer, and it will take time actually. So your customers will be in the end unhappy, and they may leave you and they move to some other restaurant because you're not able to provide them with a quick service. So you're the chef or like the computer CPU. If you're single, then you could do your work, but it's not efficient. It would take time to prepare all the dishes and serve to the customers. And multi-threading is having like a multiple chefs in the restaurant. So each working on different dishes, preparing different dishes, and they can serve it very quickly. So they can separate. So we can separate all the tasks at the same time, and they will be doing all those, preparing all those dishes simultaneously, and then you can serve to your customers, and customers will be happy. Yeah, so what happens if you do not have enough customers? Oh, enough worker in your restaurant. Customers running out of a restaurant due to the slow service. Okay, what is formally in computer terms? So it's the ability of the operating system and software application to take the advantages of the available CPU cores on your system. Basically by splitting the workload across the CPU cores that is available on your hardware, and performing all the calculation mostly independently, but it's not really, because if something is independent, then it's more sort of a parallelization rather than multi-threading. So there is a difference when there is a shared resources. So you're much more like having multi-threading. We call it multi-threading. And when there is, I would like to call when there is no independent things out there, then it's more sort of a parallelization, because then there is no shared resources, and then you need to don't need to be care about things, what's going on. Okay, let's have an example of a 10 million elements having an array. So you would like to calculate the sum of an array, which is having a 10 million elements. So you would like to write a program something like this, which is not multi-threading actually. So it's a simple program which calculates the sum of an array, and it goes sequentially calculate all this total sum of an array. Just 10 million elements. But the good thing about this problem is this: it is trivial to parallelize. It is trivial, and it's trivial to concurrency. You are able to split this problem into multiple threads, right? Something like this. You can spawn your thread between two halves of an array, and then each thread would work on half of the array and calculate the 5 million element sum on an array, 5 million sum on different thread, and then you would wait for them to complete something called wait to complete, which is not anything, by the way. It's just a join, but just it's expressed well, so it's wait to complete. And you would wait till they complete, and you'll basically merge your overall result, and you will get your total sum. So this code is bit parallelized. You can see the performance difference in between these two, the single-threaded sum and the multi-threaded sum, and see the difference in their time. So you really see that how multithreading improves performance. So yeah, it's something like this. You have single core. If you have a single core, you can run process sequentially, process 1, process 2, process 3, and then process 4. If you have dual core, you can split 2 processes in a single core, then 2 processes in a separate core. If you have a quad core processor, then you can place all those processes in different cores. So you could run them in parallel. What are the generic way to use multithreading for performance improvement? So you would divide your workload based on the number of available hardware threads. So you would partition your tasks into n smaller independent sections. N is the hardware thread. So you really like to take the advantage of the CPU hardwares that you have. And you would launch those n software threads with each handling their specific tasks. And you would wait until they complete their task, and if needed, you will combine all the results. So this is a generic way that how to use it for the performance improvement. And yes, it isn't simple as it seems. Spawning number of threads is not cheap. It's a resource-intensive task. Starting a thread is never a cheap process. It takes CPU cycles. So therefore, multithreading is much more suitable for more intensive tasks and not a small set of data, a small set of tasks. So that's the reason why it is more suitable for the more intensive tasks. So you could outweigh the benefits of it. And other things to concern about is imbalance in handling the workload. So sometimes one or more thread may take longer, complete their task, and they delay the overall CPU time. So what do you think? What's the solution for this? So if a thread taking much more time to doing its work specifically, so how do you think? What is the solution for this? Anyone would like to say? Yep, thread pool might be an option, or you basically split your workload into more pieces than there are threads. So as soon as a thread completes its work, it can fetch other tasks to execute from the queue. So basically, it's more like a thread queue. And other concern is obviously synchronizations when there are shared resources. And just believe me, your all CPU time in multithreading is just related to the synchronization problem, because if you have the shared resources, everything is concerned about synchronizations. And yeah, complexity in dividing the workloads during the computation process or dynamically. What are the use cases? So you would see use cases in web servers where you have to care about all the client's requests simultaneously. Similarly, the database system where you have to answer all the queries. Gaming, you really care about user experience in gaming, so you do not want that your graphic rendering blocking your UI thread. So you really want that each and all process happening on separate threads. Scientific computing. In the scientific computing, you have the calculations, you have the complex calculations that can be think trivially to parallelize. So you can parallelize them possibly. So it's very important in scientific computing. Financial trading, obviously, you have to care about real data analysis so quickly. And advantages is it enhances your performance, GUI responsiveness, obviously because you really want that something happening intensive in the backend should not blocking your UI thread. So for that, you could think of multi-threading. And yeah, it's parallelize the occurrences of tasks, better use of cache storage by utilization of resources, and better use of CPU resources. Disadvantages that you have to really care about, it complex the debugging and testing process. Debugging is not easy in multi-threading. Switching of context, the overall switching of context, and it increased potential for deadlock occurrences. And multi-threading is not easy. It's not easy to write multi-threaded code, so it increased the difficulty in writing a program. And you would see bunch of unpredictable results. When to use it? You just want to use it multi-threading for two reasons: separation of concerns, and other is performance. What are the separation of concerns? Consider a music application for a smartphone or computer. And this application fundamentally has two primary responsibilities. So it must stream music from the server, so it decode the audio files and play them to you without any interruptions. And simultaneously, it should respond your inputs: play, pause, next, previous, adjusting the volume. So you would like to separate these concerns to two threads. Just for an example, by the way, streaming thread and the UI thread. So one thread is fetching all the audios from the server, and other thread will taking your input and behaving based on it. Second, improving performance. So second thing when to use multithreading is you would like to improve the performance, obviously. And there's two things: task and data parallelism. Task parallelism is basically dividing a single task into subtasks so they can execute them in parallel. Very simple. Data parallelism is each thread performing the same operation on different parts of the data. So you may have seen that we have 10 million elements in an array. So you really want here data parallelism, something like this, which is it basically calling a process from taking each element from the data array. It's just 4 elements. It's not worth it here, but in much more complex scenario where you have millions of elements in an array, it would show you some results. And something to notice here is this is a for each. So it would call the process with each element from the data. And there is something special as execution pair. What it is? It's an execution policy from the C++17. It generally implies that execution for standard library algorithms in parallel. So we have bunch of standard library algorithms such as find, countif, for each. So they can leverage this execution policies from C++17. And that means all the execution of different processes will happen in parallel safely. So it says safely, but still you have to be care about synchronizing your shared resources. So it does not care about synchronization. When not to use it, complexity versus benefit. Just take these two parameters for your first basis of when not to use it. As I said, the concurrency adds complexity to your code. So it's making it harder to understand and maintain. So if the expected performance gain isn't worth, does this increased complexity give you a benefit over if you have a very less performance gain, you really do not want to use this multi-threading because it really complex your program. So if your performance isn't worth the complexity, please avoid it. Performance overhead. So starting a thread is not cheap. It has its inherent overhead. So if tasks complete very quickly, the overhead of launching different number of threads might outweigh the benefits. Remember, you have limited resources. Threads consume system resources. Too many threads can slow down your performance. It will exhaust memory because each thread have its own stack space. And it even led to resource contention because of the exhausting memory. So know your hardware, that how many cores that you get, and please do not outweigh that zone at least. But sometimes you really want it, but you're not able to do that because of something known as oversubscription problem, because it can lead to you more exhausting performance. So it's very unpredictable behavior if you try to go outside this outside the number that you get in your hardware. Potential for more bugs. So the multi-thread code is a new world of bugs actually. So you have race conditions, deadlocks, tearing, fault sharing, and whatnot. Let's look at the factors that affect multi-threading. Wait, let's have a look at something very basic, caches. But why? Because synchronization mechanisms, such as those involved in locking, are closely tied to your coherence and the consistency of memory. And many optimization techniques try to manipulate this cache coherency protocol. So you should know that how important cache is in this multi-threading scenario to enhance your performance, because it's directly related to the caches when it came to multi-threading performance. For instance, basically a locking mechanism may initially perform a read operation on a lock before attempting to change it atomically. So it should not invalidate all the caches in different CPU cores. So it helps to conserve some latency. So there is different kinds of optimizations that take this benefit. Okay, let's have a look this picture which says L1, L2, L3 cache and then memory in the disk. So you go away from the processors, so you're getting a lot of time from fetching the data from there. So, and their sizes are also gets increases as you go away from the processor. So L1 is the smallest of the size, 100 KB, L2 is 8 MB. So, and yes, these all caches are managed by hardware, and your memory and disk are managed by OS. That's why, because the thing you create in your software are software threads. That's basically handled by operating systems. So you should be very careful handling them. Okay, so some terminology that I would like to discuss is cache hit. What is cache hit? So when CPU retrieves a requested memory value and it sees that, okay, this is already available in the cache, it's a cache hit. If it's not, then it's a cache miss. So it go all the way to the memory, fetching the data, cache miss. And even though the overall capacity, we see that it's 100 MB, it's live from KB to MB. And so, but by the way, all the thing that's getting from memory to the caches, it's not come from whole KB and MB. So it just a whole block. I would say it's a block or a cache line that's get from the memory to the cache. So it's around 64 bytes in all the modern processors, something like this ACT tray. All right, so generating cache hits. So you would like to see cache hits in your program, then two assumptions that should be true. First is temporal locality. So when a program accesses a memory location, it is likely to access its neighbor locations very soon or in the very near future. So one thing that if you design your data structures, you design your application in a way so it can take advantages of your near memory blocks, so you will generate a lot of cache hits. Spatial locality. Spatial locality is pretty much similar. It's the same memory location that's going to access very soon in the near future. And if these two assumptions are not true, then sorry to say there's a lot of cache misses, and cache misses are really, really very performance inefficient, and there's a lot of things that's reloading the caches a lot. Let's have a look with the classic example how bad is this cache miss. So two-dimensional array. How does this lay out in your memory? It would go like 0, 1, 2, 3, 4, the first row, and the second row, then the third row, then the fourth, then the fifth. That's how it plays out in memory. So it's by row at a time. So for a larger arrays, not this, for a larger arrays, what would be better to calculate the sum of this, by row or by column? What do you think? Which will avoid the most cache misses? Any idea? Right. So let's look. So you have columns with a few thousand size. I initialize the array with a single element 1 to its very simplicity. And we calculate the sum by rows and the sum by columns. We write it volatile in sum. What is volatile here doing? So volatile is just for that it says to your compiler that please do not do anything with me. I'm just here, please do not touch me. And do not try to optimize me. Just here not to optimize me, please. See the difference between the column and the rows sum. So you would see the difference in their time, and it's really horrible that how cache miss can impact your performance of the overall code. Yeah, so basically design your data structure so it can take the benefit from the sequential memory order. That would avoid your cache misses. And just believe me, your hardware loves sequential memory orders. So as you can take advantage of sequential memory order, please take it because it would provide you with a lot of cache hits. Sequential memory order, something like AIJ, and if you're jumping around in the memory, it's not worth it. Okay, how different cores keep track of the cache line? That's very important. From there, we will go to fault sharing, so that's very important. So we need some sort of organizations around cores. So each core is aware of what's happening in each cores or what's happening in each cache lines. So basically, every single course have its own copy of caches. Something called MESI. Come here with the definitions: modified, exclusive, shared, and invalid. Let's try to understand this. I just keep it on a single slide to understand it quickly. So let's suppose you have two cores, and they have their copies of cache. One is cache line A, another is cache line B in the core B. So first, core A gonna fetch the data into its cache. And first of all, its data will be in the exclusive state. And the cache line status marked as exclusive. Subsequently, now core B comes up and says, okay, I want to access some memory location. Maybe it's a very similar location that has cache line A currently having. But so even you do not have the same memory region that's accessed by core B, but your variables are so much closed in memory, so they are lying on the same cache line. So when core B try to access some data from that similar cache line, and that have the cache line A also currently accessing, so now they both are in shared state. So cache line B will be in shared state, and cache line A will transition from exclusive to shared. And now, cache line B modifies the data in its cache. What's happened with the cache line A? It gets invalidated because it sees that, okay, someone modifies the data and I do not know what's that modification is. So in between the fourth step, where you see the shared and shared, because they both will be in the shared state after that. But before that, cache line B will buffer its updated values to the memory, first thing. After that, cache line A will reload its cache to get in the shared state. So this reloading and the buffering to the memory by cache line B, it will take time. And it will take some few memories, CPU cycles. So that's not really efficient, but to be aware that this saves you from getting incorrect results. So cache coherency protocol is there for saving you from getting incorrect results, because each cache should have the updated values, what's there if a cache line updates it. Last thing you just say is fault sharing, because even if you are not accessing the same memory regions, but they are on the same cache line in the 64-byte zone. So in this 64-byte zone, even if cache line A is accessing some different memory location, cache line B is accessing some different memory location, but they're lying on the same cache line. And to be aware that when a cache line B modifies it, the whole cache line will be invalid for this, because cache line B will basically block this and or lock this until it buffers it to the memory, and it will get unlocked by after that, and then thread A gets again in shared state. Pretty much in this diagram also. So the last thing you just see is fault sharing, and it is called false because the cores aren't actually needing to share this data. They just happen to locate it in so close in memory to end up in the same cache line, which have a huge performance hit. And if you believe in compiler, you would say, okay, it's not actually, I'm seeing fault sharing anywhere, because compilers are good to optimize fault sharing sometimes. And to be noted that fault sharing prevents you from getting incorrect results. So you should thankful to fault sharing because it preventing you from incorrect result. So it means that, yeah. So okay, let's have a look at the factors that affect multi-threaded performance now. Yes, the number of processors. So be aware of the number of processors, because the performance of your multi-threading code can significantly differs on whether your hardware has a single multi-core processors or multiple processors with few cores. So your program must spawn a number of threads that align with the available cores to fully utilize the hardware without leaving the processor power on the table, by the way. So let's have an example to look what I'm saying is, let's suppose you have 8 threads that can run simultaneously on your server, and if your application creates 16 threads, so you think that, okay, we have a lot of threads, then it should give me some potential performance benefit, but it will not. It might worse your performance due to the context switching in between threads, because as I said, spawning thread is not cheap. So spawning multiple thread is not something that you would like to do. Okay, so even if you like to do it, you can do it with hardware concurrency that's coming from the standard. In such cases, to correctly identify the number of available concurrent threads on your system. So you basically calculate it by hardware concurrency, then you can do your work, then you can spawn your thread based on the hardware concurrency return. Hardware concurrency, it's not as simple, so it requires caution, as it simply returns you with the hardware threads that is available on your system. So it doesn't consider other running threads or your applications. So it potentially led to your problems like oversubscription, where you find your situation you have a lot of number of threads than should be on your system. In this case, you can look through using async. So STD async is basically avoids this issue of oversubscription by aware of all the asynchronous call in your system, and it can schedule tasks more effectively with creating more threads that can handle it efficiently. The data contentions and the cache coherence traffic. We have looked at that multiple threads, when multiple threads try to read and write the same data, they can interfere with each other, and there is a lot of cache reloads, as you see. So that's also called cache ping pong happening around, and cache coherency mechanism, that a change in a one cache should reflect it in all the caches. So that might slow down your performance, but it's preventing you. I'm saying it again, it's preventing you, but it's slow down your performance. As you said, you're seeing this. There's an atomic variable shared counter. It's a global, by the way, and it's using in these 2 threads, T1 and T2, and we are using fetch add. Even if you think that we are using the memory order RELX with saying that, oh, please do not synchronize any other data, But the thing is, fetch, add is read, modify, write operations. So it would eventually doing a lot of cache reloading each time when it sees, okay, I have to do something with shared counter in each thread. So it should always reloading its cache to see, okay, what's the new value of the shared counter that's coming from different threads. Locality of the data. So the data that is accessed frequently should be kept it close in memory to take the advantage of the cache locality, as we have discussed cache locality as well. So if data is spread out in your memory, so the more time will be spent retrieving the data, which can slow down your performance. So you would see that basically provides a thread with the chunks of data, so it would lie on the same cache line as well, and it would provide you with some performance benefit because it's so close in memory. So if a thread wants to use the similar memory locations or the closing memory locations, so you would expect it to be better in performance. Excessive context switching. So if there are too many threads in the relation in your program, so operating system may spend so much amount of time, so much amount of cycles to switching in between threads, which can reduce all efficiency of the applications. So you would see that we have intentionally create 100 threads, and we're performing some tasks with a million of iterations. So it would not give you some benefit. It might worsen your performance. Let's look at fault sharing. So this, as we have discussed, that this occurs when threads on different processors modifies the variable that are independent, but they're lying on the same cache line. So this can cause unnecessary invalidation and synchronization of the caches, which means that cache have to reload after a cache updates a value, leading to this performance degradation. And it's very important to know. Consider this example, which having sum1, sum2, two threads function, and they're just calculating the sum of an array. What do you think? Where is the fault sharing happening here? Any idea? Nope. Yep. It's sum1 and sum2. It's very close in memory. So they will end up in the same cache line. So it sums the value, thread 1 and thread 2 functions summing up the value, and since sum1 and sum2 are defined next to each other, the compiler is likely to allocate on each other in the same. So basically, it's very close in memory to each other in the same cache line, basically. Oh, let's look at what's happening with the cache line. Thread 1 reads sum1 into its cache. Since the line is not present in any other cache state, so thread 1 gets it in exclusive state if thread 1 gets executed first. Next, if thread 2 comes in and it tries to look what's there, and it's tried to execute something, so it would now thread 2 will be in the shared state. If thread 1 modifies the data, basically even the sum1, it's not dependent. You can see the sum1 and sum2 is not a shared resource, but still they are lying on the same cache line. So even thread 1 tries to modify the sum1, thread 2 gets invalidated. And you're like, what? Because sum2 even not in the same location, it's just about the same cache line. So it's get invalidated, everything will reload again. So the thread 1 modification would buffers it to the memory, then thread 2 it's invalidated of course this time, and they will again be in the shared state. And after that, if you see the thread 2 modifies the data, now thread 1 gets invalidated. And this similar thing will happening again and again and again and again, and they will find each other in shared situation. Then after one are modifying, one is invalid state. So see, this someone and some is very close in memory, causing everything related to the fault sharing. And just to be noted, with the previous slides, that memory accesses may not interleave as we have described, because there might be thread 1 might gets completed before thread 2, so it might not interleave as such, but just to show you that what could happen. And yeah, it's not about the coherence misses and coherence write backs also would not like similarly like that. So in simple example, as I said, the compiler might allocate sum1 and sum2 on to the registers and not in the memory. So compiler are smart enough nowadays, so they are able to allocate them onto the registers, and they avoid the memory accessing, they avoid these fault sharing issues generally. For more complex programs, the compiler might not able to do it, and it keeps the sum1 and sum2 to memory, and leading to potential fault sharing. Those complex things could be pointer aliasing. Okay, to fix a problem that's having a fault sharing, so we need to make sure that the data that we have accessing are lying on separate cache lines. So, or you can make them to the local, or local to a function. So they are separate, they have their separate stack space. So we can update the sum2 variable like this to basically use of aligners with 64 bytes. So we can align the sum1 to 64 byte boundary, and sum2 to other 64 byte boundary. So now they are on a separate cache lines. And now thread 1 is operating on separate cache line, thread 2 is operating on separate cache line. So they are not talking to each other no more. Or you can use something coming from the standard again, hardware destructive interference size. So it's typically provide you the minimum offset between the two objects to avoid the fault sharing. It's generally 64 between the two things, but you should look in more detail. So you can use it with aligners as well. So it's something like hardware destructive interference size inside the aligners. I don't know what to do with this name. And so it would basically, if you see this structure, so in this data 1 and data 2 would lying on the separate cache line, right? Okay, so let's have a look, because this talk is more about fault sharing. So what are the causes of fault sharing? What are the programming patterns that you would find your situation fault sharing? Per threaded data arrays. So allocating an array where each element is used by a different thread. So basically you have number of threads that you build your arrays based on your number of threads can lead to fault sharing due to they are very close in memory again, something like this. So this is a typical programming pattern which is having number of threads of some array, and you're calculating some anonymous v arrays sum, and you're placing that into the sum array. So it will lie on very close to the memory, and that will cause potential fault sharing over here as well. And other is matrix parallelization pattern. So basically it causes fault sharing. So if you have multiple algorithms that work on multidimensional arrays, so which is having fine-grained divisions, which means that one thread is accessing some elements, then other thread would accessing other element, then other thread would access some other elements. So it's something like this, where suppose it like this green box is handled by a particular thread, this blue is handled by a particular thread. So this is not a way. This is actually not a good way, and this causes a lot of cache reloadings, and then obviously fault sharing. So a more nice division would be to divide your matrix something like this. So each thread operating on some number of elements in a two-dimensional array. So you are able to avoid the fault sharing. As I said, that you have too much patterns like this in your code, which is a struct field accesses with some fields and then structure. Either you can place this whole structure over some different cache line, or you're able to do that field A and field B on a different cache line with aligning them onto the separate cache line, or you can pad it so that struct would lie on some separate cache line if you have multiple structures in your code. Yeah, it's dynamic memory allocations and fault sharing. So when a program dynamically allocates memory for the small object, so it basically risks placing the data by concurrent threads very closely, and so obviously in the same similar cache line. And what is the way to mitigate this problem is to allocate larger memory blocks for a thread's exclusive state. So instead of allocating each small object separately, which might scatter them across the same cache lines, allocating a single large array can localize a thread's data, reducing the chances of cache line collision or the fault sharing. And else, if possible, aligner objects with aligners or the hardware destructive interference size. All right, so we have a lot of algorithms in standard that enabled multithreading. So many algorithms in the standard library have their parallel versions. What? Including sort, find, replace, countif, for each, etc. And to use them, you will call it in the same way, but just with a new parameter called execution policy. For example, how do you sort parallelly? Just use execution par in your array from begin to end, this range. Yes, so that's all. Final summary would be from my side is multithreading is indeed not easy. It's not easy to write multi-thread code. You have to concern about a lot of things. Other is spawning thread is not cheap. So synchronizations as well. It's not cheap. Even there is no contention in your program. Even there is no shared resources. So even you do not have multiple thread accessing the same data, and multiple thread try to lock and unlock the same mutex, but still the mutex have the high contention. So you have to think the other solutions for that. Might be shared mutexes, which Victor presented in his last talk, or you might be using some better synchronization primitives like latches, barriers, but you need to be very careful about it, because which synchronization primitives you try to use. Or, this point is very important, best synchronization is no synchronization. Avoid synchronization if you can. It's not my words, by the way. So avoid synchronization, because everything related to your multi-threading performance is synchronization again. And if possible, use standard library to parallelize. For example, the transform and reduce, because these algorithms are trivial to parallelize. You can use your different algorithms with the help of this transform and reduce, and you can see that, okay, this could help me parallelize my problem. Or you can use C2C Linux perf tool, cache-to-cache Linux perf tool to detect such problems like fault sharing. And at the end, you could do nothing but just believe in compiler that, okay, this will optimize it. I am not going to care about it. So be it like that. All right. Richard Feynman, my favorite scientist, by the way. And you can keep in touch with me on Twitter. Just a disclaimer that I do not post much about tech, but more about science. So yeah, thank you so much for listening to this talk. Okay, any questions?
Hi.
Hey.
Just to clarify one thing. If I have an immutable data structure, so const in C++ words, and I share that with multiple threads, can this alone incur false sharing, or is it okay if it's read-only?
It's okay if read-only.
Okay, thanks.
Yep.
I've got some questions from our online listeners. First question is if there are any points with respect to avoiding cache misses to be aware of while designing data structures that are going to be residing in heap memory.
Sorry, can you repeat?
Yeah. Are there any points with respect to avoid cache misses to be aware of while designing data structures that are going to be residing in heap memory? So is there anything we should, if I understand that correctly, the question is asking whether there's something we should consider when designing data structures for heap memory for the alignment regarding cache misses. I'm not entirely sure it's an online question, so I might be misrepresenting it.
I do not get it actually, but what I think is, so you try to see that cache misses to be less, right?
I believe so, yeah.
Yeah. So it's just about to use your data structure that it can take benefit from the sequential memory order. So see your data structures if it provides your sequential memory locations. So yes, it would take benefit and would avoid cache misses in such cases. So yeah.
Okay, thank you.
Okay, thank you. Okay, any others? Okay, thank you so much.